Hello and welcome back. So speaking of momentum, as a way to just get us going, here's an object, and similar to how this point mass has, well, a mass m and a speed v, or a velocity, let's say, and therefore momentum, whoops, vector. This rotating object that doesn't translate, this object has a translational velocity, but this rotating object has a rotational angular velocity, right? And it has a mass m, but it also has, well, a distributed mass, and therefore we're not worried about only its mass, we're worried about, well, its resistance, not just to linear motion, but its resistance to angular motion or angular acceleration. So this thing has a rotational inertia I and an angular velocity omega. And therefore, we say that this rotating object has an angular momentum that is, well, defined to be L, the product of I and omega. We don't really need this in general. That's the in general. Delete. Okay, so what I'm hoping you can see is the analogy that we're drawing from point mass translational velocity to distributed mass angular velocity. All right, translational, well, yeah, this is translational, this is rotational. Okay? So if objects are rotating, they have angular momentum. Just so we're sure, typical units for angular momentum, you remember that rotational inertias are typically something mr squared, some fraction mr squared. And so m r squared, omega measured in radians per second, but the radians don't really count as a unit. So there's your units, kilogram meters squared per second. Fair enough? Okay, great. Now, right, here's our object, mass m, velocity v, right, our linear momentum, product of mass and linear velocity. All right, this object, while it's not rotating, it's a point mass, it can't rotate. It's not even moving around in a circle. But look, here's this, oh, hello. Here's a point in space P. All right, well, what we can say is, where is our mass M? Well, we can locate it relative to any other place we want. In this case, I'm choosing to locate this point relative, this point mass relative to point P. And I do that by use of what's called a position vector, R. R does not mean radius. R means vector from arbitrary point in space to another point in space, in this case, the location of an object. So R is vector from any point P, let's call it, to our object's position. Well, there's a definition, another definition of angular momentum. All right, and that definition is a vector equation, just like this is a vector equation. All right, and that vector equation is that angular momentum is, well, we write it like this. R, not times, but R cross P. P is linear momentum. All right, now that looks a little bit like, I'll kind of go sidebar over here. It looks like that. Now, my guys don't talk a ton about the vector nature of torque, or this idea of, that doesn't mean times, it means, it's called a cross product. But the bottom line is, these have similar forms, right? One vector equals the cross product of two other vectors. And a lot of us know that in order for a force to produce a torque, the magnitude of the torque can be found if and only if there's a component of force that's perpendicular to vector r. Or we can look at the component of vector r that's perpendicular to force F. All right, well, the same sort of thing happens here. All right, because by definition, in order for a cross product to have any non-zero magnitude, one component has to have, or sorry, one vector has to have component perpendicular to the other. All right, in this case, our velocity is entirely perpendicular to this vector r, and velocity lives in, this is really saying r cross mv vector. You can take the m and pull it out in front if you want. All right, but the idea is, for an object, I'll keep moving this, for an object to have angular momentum relative to some point in space, well, what must be true? We can find the magnitude of that angular momentum by looking at r times, the magnitude of r, literally what distance this is, times m times the component of v that's perpendicular to r. Or we can look at the component of r, its magnitude, that's perpendicular to v. Same thing. Okay, and these are two different ways of talking about angular momentum. One is typically, for an object that's a distributed mass, an extended body that is rotating, let's say, about an axis. It's in a lot of cases appropriate to talk about that object's moment of inertia and how fast it's rotating. Right? In this case, this is not an extended body. It's not rotating. It's not even moving in a circle in this case, but this is a definition of what angular momentum is. And if you notice also, well, if we go back to here and say that angular momentum is I omega, for this point mass is angular, or moment of inertia, rotational inertia is mr squared. In this case, r means the radius of its path, of its circular path. This thing actually isn't moving in a circle, but we can say it's kind of how far it is away from this point, right? And omega, mr squared, that's rotational inertia. And omega we can write as v over r. So look at this, we get to go back to, mrv, same as mvr. Right, so those two expressions are actually equivalent. The two expressions being r cross p and I omega. All right, one other neat thing to look at here is, let's take this object at some later instant. Yes. Now it's over here. It's kept moving. All right, well, check this out. Now, there's some new vector, oh boy, there's some new vector, better, r prime, right? But this object has just kept going in a straight line, right? Well, if we want to look at this object's angular momentum now, so here, initially, when the object is here, when we say m or rm v perpendicular is just v when these are perpendicular. So now this thing, that's a right angle, not an L. So right now this object has an angular momentum mvr. Okay, now what we have to do is look at the component of v that's perpendicular to r. All right, so what we can say is, let's see, here's the general direction of r. We want the component of v that's perpendicular to that. So there's that. This is what I would call v perp. All right, and this angle here is the same as that angle there. Is that true? Yep, that's true. All right, so check this out. The angular momentum now, I'll call it L prime, is R prime mv perp. Agreed? So L is R prime m. Now, v perp right here is v cos theta. Agreed? So we get R prime mv cos theta. The angular momentum was mvr, but check this out. What is this r? Well, look, here's a right triangle with r prime as a hypotenuse and r adjacent to this angle. So r is r prime cos theta. So look, we either get r prime mv cos theta sometime later, or in the beginning, mv r prime cos theta, and those are the same thing. We're just multiplying things in different orders. But what that shows you is something pretty neat, that in a very basic sense, since this object just does what it was doing before, it experiences no net force, this object maintains a constant velocity, a constant linear momentum, but also, relative to this point, this object maintains a constant angular momentum. Right? And that, at a very, very basic sense, or basic way of saying it, is that angular momentum, as long as nothing happens, angular momentum is conserved. It's constant. All right? And we'll look at some situations like that that aren't just an object moving in a straight line, but this is a good place to start with the idea that as long as nothing happens, angular momentum is conserved. All right? Let's make some analogies. Draw some analogies between linear stuff and angular stuff, or rotational stuff. All right? There's certainly, from a kinematic standpoint, we can say things like, for example, right, on the linear side, we've got things like delta x is v naught t plus 1/2 at squared. Well, on the angular / rotational side of that analogy, we'd say something like delta theta, sorry, is omega naught t plus 1/2 alpha t squared. All right, when we look at, dynamics, things having to do with forces, we can say, the very most basic linear statement says net F is ma. Right? When we translate that to an angular or rotational context, we'd say something like net torque is I alpha. All right? When we get into momentum stuff, we typically turn this into something a little different, like, well, maybe net F. I'll just leave it as F. It's, depending on how you want to look at that. We can say this turns into something like F delta T equals M delta V. Well, we can now translate that over here and say, well, let's see, net torque times delta T equals I delta omega. Right, and if you remember, these are ways of calculating an object's change in linear momentum. Well, guess what? These are ways of calculating an object's change in angular momentum. All right, when we get to energy, right? We have on on the linear side, things like, well, k is 1/2 mv squared. On the angular rotational side, we have things like, well, this is a k translational. Here we have a k rotational 1/2 I omega squared. All right, so this just, what we're trying to show you here is that there's just, another analogy that we can draw between linear stuff and rotational stuff. All right, this is about kind of filling out that set of tools we have. All right, so let's look at a couple of specific sort of cases. We got a kid riding on a merry-go-round that we'll treat like a disc, right? And this disc rotates about that central axis. All right, the disc, we'll say, has a mass, capital M. We'll say that the kid has a mass, little m. We'll say that the disc has an overall radius r. And we can locate this kid relative to this central axis with a vector. Let's say he's r, a distance r away from that axis. All right, so if we want to talk about the angular momentum of the kid, there's two ways to do it. One is to say I of the kid times omega, and that's going to give you, let's see, I of the kid is little m r squared omega. And remember, this omega we can write as v over r. So we could write this as mr squared v over r, and that gets you to that mrv or mvr. So either way you want to do that, they're equivalent. Okay? If we're talking about, the fact that this merry-go-round is rotating, we're probably going to end up talking about the angular velocity omega that this whole system has, and every part of that system has the same angular velocity. All right? For the merry-go-round, it really is the most appropriate GR to talk about the merry-go-round's moment of inertia, rotational inertia. So this is a disk, right? So that's going to be 1/2 big M big R squared omega. All right, so if we wanted to talk about, hey, here's a kid riding on this merry-go-round, we could talk about the system's angular momentum as, I'll write it as little m little r squared omega plus 1/2 big M big R squared omega. And maybe we say this is the same thing as really saying here's the combined moment of inertia, the system's rotational inertia times omega. Okay? Fair enough? So this is the system's rotational inertia. Fair enough? Okay? Now, how about this? What if a kid jumps onto a merry-go-round? Well, I call this a two-object interaction. So what must happen? Well, we've spent quite a bit of time now talking about here's an object. We'll call this, object 1, moving at this, with that momentum, say, and here's object 2, moving with that momentum, and these things interact. What does interact means? It means apply forces to each other. All right? We know that things like, well, the force that the first one experiences is equal and opposite to the force that the other one experiences. And the amount of time that each one experiences that force is equal. So we can say that, well, this says their impulses are equal and opposite. Delta P1 equals negative delta P2. And this gives us a way to say that the net delta P is 0. And this says, all right, linear momentum is conserved. If impulses are equal and opposite, changes in momentum are equal and opposite, it means the total change is nothing. And when objects that are translating interact, linear momentum is conserved. Well, in our new context, kid and merry-go-round, kid jumps on the merry-go-round, there's rotational things happening. And the kid interacts with the merry-go-round, not just yes or no interacts, but interacts at a specific place. The kid applies a force to this object at a certain place. There's a force applied to the kid at a certain place relative to this axis. All right, and so what we say here is that it's not just that the forces that each of these objects exert on each other are equal and opposite, but the torques that each of these objects experience are equal and opposite. Negative 2. And that's because this is R, F1 is R, or negative. Well, it's really probably best to say R times negative F2. So the forces are still equal and opposite, and guess what? They happen at the same place relative to some other place, which typically is relative to the central axis. And we can also say, well, that the interactions, the torques are experienced for the same amount of time. So R, F, you know what? I'll just go back to this. I'll say torque 1 delta T equals negative torque 2 delta T. Well, remember, torque times delta T, we got to go back a little bit, but torque times delta T is a change in angular momentum. So this says that when objects interact, one of them experiences one change in angular momentum. The other one experiences an equal and opposite change in angular momentum. And that means that the net change in angular momentum, I'll say system, and I'll say system is also 0. And this says when two objects interact, well, I can't write angular L. Like I shouldn't have really written linear P. Let me go back here and just write momentum is conserved. Angular momentum is conserved. So hopefully not a huge surprise that, you know, we've talked a bunch about momentum being conserved. Well, it's true in both translational and angular situations. So let's look at a couple of examples. All right, let's say that initially this object is rotating, the merry-go-round is rotating with an angular velocity, let's call it omega naught. All right, the kid is dropped onto this merry-go-round. So here's what I would write this like. I'm going to say, well, the net L initial has to equal the net L final. This is a conservation of angular momentum statement. So we might say like L merry-go-round initial plus L kid initial equals L merry-go-round final plus L kid final. The kid, just before contact, is moving this way. The axis about which this system rotates is right there. And so, well, moving this way doesn't give this kid any angular momentum in the direction of the rotating disk's angular momentum. So we can get rid of this. That's a little hand wavy to say that. I mean, it's definitely true, but the angular momentum that the kid has, yeah, it's really relative. Yeah, it's relative to this axis. All right, so relative to this axis, yeah, the kid has 0 angular momentum. All right. In the end, these two things, well, this is like a hit and stick. Okay. So if I say this, we could turn this into I merry-go-round omega initial. Well, we call that omega naught, right? Omega naught equals I merry-go-round omega final plus I kid omega final. No, I should say merry-go-round final, kid final. Except, let's assume that kids, this is kind of a hit and stick, right? The kid ends up rotating with the merry-go-round. So what we're going to do is turn this into I merry-go-round equals, well, I merry-go-round plus I kid times their common final angular momentum. Right, and then we say something, well, we haven't defined all the terms, but if we were to say that, like we did before, this has mass m and the kid has mass little m, and this is radius big R, and the kid hits this surface at a distance little r from the center, then we can sort of get where we got before, where we say this is a disk, 1/2 big M big R squared omega naught equals 1/2 big M big R squared plus the kid little m r squared, he's a point mass, times omega final. Right, we could solve for omega final. Fair enough? Or we could solve for whatever we want to solve for. But typically, that's a very common one. What's the system's angular velocity now? It's got to be less than it was before, because the system's rotational inertia has increased. Okay? Here's a different one. This merry-go-round is stationary. All right? Kid runs this way and jumps onto it. We don't really, we should disregard this. I mean, it's true, but we've already sort of developed that, I think, in a better way. Anyway, here's kid, mass m, speed v. Here's r. Here's, this thing has a mass, big M. All right, kid runs and jumps on. All right, well, again, we conserve angular momentum. We say merry-go-round initial, kid initial, merry-go-round final, kid final. In this case, it's the merry-go-round that has no initial angular momentum. Right? The kid does have angular momentum. Right? The kid, there's a point, an axis of rotation really that we're interested in where the kid is relative to that. And really when the interaction happens, the kid ends up here with that speed. And the r that we're, really the r vector, in this case from our point of interest, that axis of rotation, to where the kid is, looks like that, and we get a nice right angle there. So that means that the kid's initial angular momentum, I would write as mv, r, right? Assuming the kid hits right at the outer rim of our merry-go-round, in this case. Okay, equals, I'll do the same thing. This is going to be, well, let's see, how do we want to do this? Well, maybe we do say 1/2 big M, 1/2 big M R squared plus, here I'd probably write this as the kid's point mass. Oh, I forgot omega. Omega final plus little m r squared omega final. So now I'm, notice I wrote angular momentum here as mvr and here as I omega. It's okay, they're the same thing, right? Is it better or worse to write it in a different way? I guess it depends on what you're given, right? But it would be pretty likely that you'd get this kid's initial speed, a linear speed, v. All right? And like we did over on the left side, We can say that the kid hits and sticks here, so we get something like little mv big R is 1/2 big M R squared plus little m R squared I system at common omega final. Right, and again, what do we want to solve for? I don't know. But this is an expression that talks about initial angular momentum, final angular momentum, and that they're equal. It's conserved. Fair enough? Okay, here's another example. This is a top view of a door. All right, hinge is here. And let's say door has mass M and width W. Here's the top view, right? So here's the door, hinged here and here, door. Someone throws a snowball that way at it, and it sticks to the edge and pushes the door open. Okay? So let's see. We'll say this has a mass little m and a speed v. This has a mass big M and a width W. Let's find or express for omega final. What you should do is show that this system ends up with a final angular velocity equal to little mv over w times little m plus big M over 3. Yeah, got it? That's your job. See you next time. Bye-bye.